Question 6 is an analysis question. So we're told that mass spec and infrared spec are used in analysis. And the first part of the question is all about sulfur, the element sulfur. And we are told that it exists as N molecules. So N is going to be a number. So we've given the mass spectrum, and straight away you can see I've highlighted this peak here. The peak furthest to the right, I will say, is the most important peak because it tells us the MR of the substance. So, and it's called the molecular ion peak. So the M over Z value for the molecular ion is 256. Suggest the formula then of molecule of sulfur. Nearly give the answer away there. So we know the whole thing was 256. The mass of one sulfur is 32.1. So divide the 256 by 32.1, the mass of one sulfur, we get 7.975. So it's obviously S8. The formula for the fragment ion with the M over Z value of 128. So the ion, positive ions always in mass spectrometers. So it's got to have a positive charge. So 128, what could have caused that? Well, we need to divide that 128 by 32.1, the mass of one sulfur, 3.99. So that must be due to the S4 plus fragment. So then changes tack now. Element L is analysed using mass spec. There's the mass spectrum there. So these are all isotopes now. These aren't fragment peaks, these are the individual isotopes. And we've got to calculate the relative atomic mass of L to 1 decimal place. So it's percentage abundance times the mass of the isotope, plus that one, plus that one, plus that one. So you can see the calculations at the bottom there. And that comes out at 195.16. So to 1 dp, that's 195.2. Given everyday use for IR spec, so I always say to my students it's used in breathalyzers to test the alcohol content in a driver's and motorist's breath. You could also have said monitor air pollution or drug detection. So for example, in the Olympic Games, when an athlete's blood or urine is taken, you could test for drugs using IR spec. So it's moving over to infrared now. So we've got a solvent M, organic compound used in paints. It's got an MR of 72. We've got some percentage composition mass. So straight away you can be thinking, well, I can calculate the empirical formula from that. I've got the MR of the molecule, so I'll be able to work out the molecular formula. And we've got the infrared spectrum. So highlighted this straight away. Giveaway there, you've got a C double bond O here, and the fact that there's no broad absorption here, straight away you know there's no OH. So it's looking like this is either an aldehyde or a ketone. So suggest with possible reasons 2 possible structures for M. Well, I've just said it could be an aldehyde or a ketone, so that's why there's 2 possible structures, I'm guessing. Let me just, yeah, sorry about the gap there. So percentage composition data allows the empirical formula calculation. So table, we've got the percentages divided by the relative mass of each of the atoms, and there's the moles. So 5.56, 11.1, 1.39. Divide all of these by the smallest to get the simplest whole number ratio of the moles. So it's 4 to 8 to 1. So the empirical formula must be that. Next thing you would need to do is check what that adds up to. So it actually adds up to 72, which is the MR of this molecule. So the molecular formula must be C4H8O. The IR data told us that there's a C double bond O. Make sure you tell the examiner how you know. Peak at 1700 centimeters to -1 indicates the presence of a C double bond O. And it might be worth putting that. The fact that there's no broad peak in the 3000 region means there isn't an OH in this molecule. So then you just got to play around with the atoms and try and get it to fit. So there's the aldehyde that would fit with this data. So that's butanal. There's the ketone there. And the final thing is it could also be this branched isomer. And that's why I had that pause there, the two possible structures. If they'd said it was branched, oh, that wouldn't work, would it? Because that's not branched, right? Sorry about that. So there's your three possible answers.